So thus far, we have looked at the colligative properties, and we define them as properties of a solution that depend on the number of particles of solute. In other words, essentially the concentration of the solution, not on the identity of the solute per se. And the first one we discussed was vapor pressure, and we talked about the different influences that the energy and entropy have on the process. All right. So let's go ahead and go to our next topic here. We're going to go now to our next one. And this will be the boiling point elevation. So let's go back to the definition of what the boiling point is. Remember that we said that this is the temperature at which the vapor pressure above the liquid equals the atmospheric pressure. So essentially, the vapor of the liquid has equalized pressure with the air around it. Now, it's interesting. Of course, we know that water boils at about 100 degrees Celsius at 1 atmosphere pressure. If I mix 100 grams of water with 34 grams of sugar, the boiling point goes up to 105 degrees. Notice that? In other words, the presence of the solute makes the water boil at a higher temperature. Let's explain that. Remember, we already said in the previous section, when you have a solute, the vapor pressure decreases. Remember that in order to reach the boiling point, you have to essentially go up to the same as the atmospheric pressure. But in order to re-equalize the vapor pressure with the atmospheric pressure, we need to supply energy, right? We don't have to put more energy to get that done because you're starting from a deficit in vapor pressure already. So as a consequence, by the time the liquid boils, by the time the vapor pressure equalizes the outside pressure, you are at a higher temperature than you should be. So that is kind of in a nutshell an explanation for why the presence of the solute elevates the boiling point. It has to do with the decrease of vapor pressure and the need for more energy in order to catch up to the atmospheric pressure so the liquid can boil. Well, just like the vapor pressure, we have a formula to calculate the boiling point elevation. And we have it here, delta T equals Km. Let's see what these things are. So delta T is going to be the increase in the boiling point. We can put a subscript B in there just to remind us that we're talking about boiling. That M there is not the mass, it's the molality of the solution. Remember, we talked about molality last, first lecture. And we said that this is many times the preferred method for writing out concentration when we're going to be going through temperature changes, because since molality has to do with moles to mass ratios, those don't get affected by temperature like volume does, and consequently the other unit, which is molarity. And then KB is something called the molal boiling point elevation constant. As a mouthful there, just a constant in degrees Celsius per molal. Now, the constant is particular to each solvent. Remember, the boiling point elevation just has to do with the molality. In other words, the amount of solute in there. But it's going to depend on which solvent it is. So you had to put in a constant for the particular solvent. Okay, let's do a little practice problem here. If you add 4.36 kilograms of ethylene glycol, there's the molecular weight, 62.07, to 6.50 kilograms of water, what will be the boiling point of the resulting solution? And here's the Kb constant for water, 0.52 degrees Celsius per molal. Okay, again, let's use our equation. Let's see what we need to find out. Well, the first thing we need to do is we need to find out the molality, right? So let's start out by calculating the molality of the ethylene glycol. It says here we have 4.36 kilograms. Let's go ahead and change that to grams. So 4.36 thousand or times 10 to the 3 grams. We know that 1 mole of ethylene glycol is 62.07 grams. They told us that in the problem here. So that means that we cancel out the units of grams. And punch the numbers into the calculator. Adjust for sig figs. And this comes up to be 70.2 moles of ethylene glycol. Now to calculate molality, we have the ratio of moles of solute to kilograms of solvent. And this is very convenient here because they gave us the weight of water instead of the volume. And so we don't have to convert the volume into grams. We have straight up grams. And so we have 70.2 moles of ethylene glycol in 6.50 kilograms of water, which is the unit you put for molal. And moles per kilogram, that gives us molal, and the concentration is 10.8. All right, but we're not done yet. We're just trying to calculate the molality. We want to find out what is the change in the boiling point. Remember that the equation gives us delta T, in other words, the elevation of the boiling point. It doesn't tell us what the boiling point is, it just tells us what the change is. So you have to know what the normal boiling point is anyway, which for water is 100, right? So 0.52 Celsius per molal, that's what the kb of water is, times the molality, 10.8, that's 5.6 degrees Celsius. So that's the elevation of boiling point, the increase in the boiling point. So if the normal boiling point is 100 and it increases by 5.6, that means your new boiling temperature is 105.6 degrees Celsius. Let me give you a few seconds while you finish writing your notes. Be aware you have several practice problems in your homework, so make sure you get those done so you can get a little more practice with these things. Again, notice that I could make a solution, measure the boiling point, and knowing the solvent's Kb and the change in the boiling point, I can kind of go back and calculate what is the molality of the solution. So this is in case we're working with an unknown. Seems to be like a cumbersome process, but like I said, mathematically, you could solve for any one of these variables in here. You could even use a table of molalities versus delta T to find out what is the value of Kb for a particular solvent. Like I said, whenever you have 3 variables, given any 2 of them, you should be able to calculate the third one. Now, any applications of this at all? In other words, or is this just a chemist's little toy box here? No, actually, this is a very important application for this boiling point elevation. A commercial mixture of ethylene glycol and water, so not the one that we just did, but one you buy at the store, boils at 120 degrees Celsius. Why is this useful? Aha, I think some of you know. This is what we call engine coolant. That's right. You either buy it or you have your auto service shop replace it for you when they do your checkups, right? And the idea is, particularly nowadays, where you have these very high performance engines, they can reach very high temperatures, higher than 100 degrees, which means that water by itself it's not going to be sufficient to keep the engine from overheating. So what you do is you spice it up, right? You kind of like go in and put some ethylene glycol, and a mixture of water and ethylene glycol now boils at a higher temperature, which means that the water is going to absorb more heat without boiling. It'll stay liquid, and therefore it can still keep being flushed through your system and keeping your engine cool so the components don't start melting down or whatever. All right. Now, you know what's interesting? The same or similar mixture that we use as coolant, at least here in California, where for the most part of the year we have, warm weather, maybe a few exceptions for those of you who live in the mountains, is that the opposite is also true. In other words, this same substance can be sold as coolant, but it can also be sold as antifreeze. And that brings us to the next colligative property, the freezing point depression. And no, this is not a psychological issue, okay? Depression means like lowering. So remember that the freezing point, we said, is a temperature. It's the temperature at which the liquid phase is in dynamic equilibrium with the solid phase. This is the point at which the rate of the liquid freezing equals the rate of solid melting until the temperature or the energy you've removed, the energy you've removed is sufficient to basically move everything in the direction of freezing the liquid. So here's what's interesting. Of course, we know that water freezes at 0 degrees Celsius, but if you have this mixture of ethylene glycol and water, it'll freeze at under or minus 20 degrees Celsius, 20 degrees below the normal freezing point. In other words, the presence of the solute decreases the freezing point. And again, we have an equation for this, very similar to the one we just discussed for the boiling point elevation. It's proportional again to the concentration, right? So once more, you have delta TF, in this case for freezing, would be a freezing point depression constant, which is particular for every solvent, times the molality of the solution. I don't have a practice problem for this one because essentially the math is very similar to what we just discussed. So notice that a mixture of ethylene glycol and water will both elevate the boiling point and also decrease or depress the freezing point. It goes both ways. Let's go ahead and explain this from the point of view, again, of our other two actors, energy and entropy. Okay, we start out with the liquid solvent. And remember, when we freeze it, we are essentially causing the particles of the substance to fall into a more highly ordered, less movable set of positions. Now, in order to accomplish this, we had to remove kinetic energy so that the potential energy of attractions could take over and pull the molecules together, right? So in other words, freezing requires energy removal so that the particles can settle into the more ordered solid state. Notice that because you're going from a less ordered to a more ordered state, in other words, a more random to a less random state, you essentially have a decrease in entropy. In other words, delta S is negative. Remember, we said S is the standard symbol for entropy. Again, let's consider now the solution. When we build the solution, we said that now, because the particles are more randomly distributed, you actually start at a higher level of entropy. The solution is more disordered. So in order to bring it down to the level of order of a solid, what's going to happen is you're going to have to take a bigger entropy change in the negative direction. In other words, If the entropy change from liquid to solid was not favorable because it was negative, this one is even less favorable because it is more negative. Since you're fighting against nature's tendency of wanting for entropy to increase, that means that we're going to have to require a greater energy removal because we had to overcome what is essentially a less favorable entropy change. And that explains why by the time you're able to achieve the solid state, you have had to travel a longer path of entropy decrease. That means you had to remove more energy than you did with the pure solvent, and therefore you're arriving there at a lower temperature. And that would be the new depressed freezing point. Okay? So once more, many of us don't have this experience. I never had it because I grew up in the tropics anyway. But I did live in New England for many years. That's where I got my grad school education. And that's when 3 of my kids were born there. So it was very common in the wintertime to see these trucks sprinkling salt on the streets, kind of like that. And you can tell that this is dead of winter, a lot of snow. Like I said, many of us here in Southern California don't get to experience this unless we go take a little trip up to the slopes or Big Bear or whatever. So what is the salt for? Well, think about it. If the presence of a solute decreases the freezing point, that means that water is now going to freeze at a lower temperature. So if I am slightly above that new freezing point, let's say the freezing point would have been minus 20, and the temperature is super cold, but it's only minus 10 degrees Celsius. That's funny. Only minus 10. That's pretty cold, actually. But therefore, the water at that temperature now will stay liquid. It melts. So there's less ice on the road. So this is done to prevent, ice from building on the roads and accidents happening. Have you guys seen how, for example, chefs, when they're boiling water for, let's say, pasta, for example, once they boil it, they add salt? It's not only to season the pasta, it's also to increase the boiling point of the water. To increase the boiling point of the water. In other words, water is now at a higher temperature when it's boiling, and therefore it cooks the food a little faster. All right. Now, one thing that we haven't talked about is, what if the solute is, for example, an ionic compound? We talked about salt here. Does that impact? Remember that colligative properties are related to the number of particles, not the identity of the solute itself, right? Oh, sorry, I had that line in there. I crossed that out because I was supposed to give you a demo about ice fishing, but there's no way I can do that in my home office here with a little laptop and whatever. So I'll work it out at some point, and maybe if I can get it done by the weekend, I'll post it on Canvas. If not, come and see me next year. All right. What if the solute is an electrolyte? Let's think about this. Remember that electrolyte is a substance that when you dissolve it in water, allows a solution to conduct electricity. So if I take water and I stick a light bulb with 2 non-connected electrodes in it, I don't get any light to turn on. But if I've made a solution with an electrolyte, the light turns on because there's electrical energy being conducted. You remember that from, what was it, Unit 4, right? Now, let's contrast 2 different kinds of solutes. Let's consider first methyl alcohol, or methanol, CH3OH. It's soluble in water. It's actually very soluble in water in pretty much any proportion you want. But notice that the chemical equation we write for the process, the only thing that changes is the physical state from liquid to aqueous. There is no change to the integrity of these molecules of CH3OH. So 1 molecule of liquid gives you 1 molecule of dissolved solute. But what about sodium chloride or salt? Well, when I put salt in there, each unit of NaCl becomes 1 unit of sodium ions and 1 unit of chloride ions. So in terms of the numbers of particles in the solution, notice that we have duplicated them. We don't have 1 particle per unit of sodium chloride. We have 2 particles. And since colligative properties have to do with the numbers of particles, you can see where 1 unit of CH3OH dissolved in water is not going to have the same effect as 1 unit of NaCl. NaCl should give you twice the effect, right? Each mole of NaCl produces 2 moles of ions in solution. So when dealing with colligative properties, we have to put in a correction, not for the type of solute in the sense of its identity, but the type of solute in terms of whether the substance is an electrolyte, and we had to start considering, well, how many particles are being produced once the solute dissolves. So we're going to introduce here something called the Van Hoff factor. This would be the actual number of particles in solution after they've dissociated, divided by the number of formula units that were initially dissolved. For example, we said, NaCl, right? We said 1 unit of NaCl gives me 2. So presumably the Van Hoff factor would be 2 particles for every formula unit. That'd be 2. So that'd be the Van Hoff factor. And we use the small letter I to represent it. So let's build a little table here. Let's consider a non-electrolyte, and let's see what I should be. So a non-electrolyte gives you 1 particle per formula unit, right? 1 CH3OH for every CH3OH that you put in. So the Van Hoff factor I should be equal to 1. What about NaCl? What should it be? Okay, so here is where you go back to your, knowledge of ionic compounds and remember, okay, so when this dissolves in water, I get 2 ions for every formula unit. So 2 over 1 should give me a Van Hoff factor of 2. Okay, what about this one? Calcium chloride. What would you predict the Van Hoff factor to be for calcium chloride? Okay, remember, it's not the types of ions, it's the numbers of ions you get. So you get 1 calcium and 2 chloride ions for every formula unit. So that means you have 3 over 1. That would be a Van Hoff factor of 3. Now, just so you know, although we are using this very simple approach to it, it doesn't work that way. Because in a real non-ideal solution, it may be that not all of these particles are actually active in the process. So if you guys ever take a upper level chemistry course like analytical chemistry, you're going to learn that really what a chemist measures is what's called the activity of the substance, not the concentration. We've pretty much assumed that 1 NaCl unit dissociates into 2 sets of ions, right? But it may be that in reality, what you get over the whole sample of solution is maybe a factor of about 1.9 maybe, or something like that, because these are not ideal solutions. So what we need to do then is, since all these colligative properties are related to the numbers of particles, we need to add a factor to our calculations. So for boiling point elevation and freezing point depression, we're going to add a Van Hoff factor to each one of those equations. So on the left, we have delta T, the boiling, and on the right, the delta T of freezing. Notice that we've added that factor. So that means that an electrolyte will typically increase the change in either boiling or freezing point. It'll make the boiling point elevation broader, the freezing point depression more remarkable. Okay, so that's why on the roads in Massachusetts where I was living, They put salt down on the road. They don't put alcohol. Sorry, I couldn't resist. Okay, let's look at the final colligative property. This is the osmotic pressure. So you guys have heard this word, right? We use it a lot in our society, mostly with a kind of like a funny kind of side to it, right? Osmosis, because everybody learns in school what osmosis is. So I'm going to go very quickly over what it is and then give you a formula that we can use very, very interestingly. So osmosis is the selective passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated one. So here's a sketch of what's going on. All right. So I have two chambers, and these two chambers have two solutions of different concentrations. Okay, the one on the left is more dilute, and the one on the right is more concentrated. As you can see on the sketch on the right, what is happening is the separation between these things is actually due to what's called a semi-permeable membrane. It allows the passage of solvent molecules but blocks the passage of solute molecules. In the sketch, essentially what we've drawn is a membrane that has pores in it, and the pores are small, so solvent molecules can go across, but solute molecules are prevented from going across because they just don't fit. Remember, on the right side chamber, the solution is more concentrated. In other words, it has more solute molecules. Technically, that means it has less solvent, technically. Now, the solvent is going to move back and forth. There's nothing really driving the solvent to move specifically from the more dilute to the more concentrated solution. It's simply doing it randomly. Remember entropy. Particles want to distribute themselves randomly. Now, the thing is that because there are more molecules of solvent on the left side, when you add up all of the different back and forth movements, the net movement ends up being from left to right, from the more dilute to the more concentrated, from the one that has more solvent to the one that has less solvent. As a consequence, what you get is, you get up here, if I had attached tubes at the top of each one of these containers, I can see where the level of liquid on the right side, on the chamber that was more concentrated, has increased. That's because there's more net liquid moving from the dilute to the concentrated side than from the concentrated to the dilute. And so you end up doing that. Now, if I could come back here and put a piston in that tube on the right side, and then attach that to a pressure gauge, and I could measure how much pressure do I need to add in order to push the liquid back to where the two levels are the same like they're on the left side. That pressure is going to be the osmotic pressure. We call it pi. Like I say, guys, scientists just love these Greek letters. So why call it P or anything like that when you can use a Greek letter and call it pi? So that is the osmotic pressure. Now, some people might say, well, can you just measure the difference in height between the two columns and say, oh, well, those millimeters, that's going to be the pressure. Well, you could if that were mercury you're working with, but remember that our torr or millimeters of mercury scales are based on mercury. This probably is not mercury. I hope it isn't, because it looks kind of dangerous to work with that much mercury. This would probably be water or alcohol, or maybe like a nonpolar solvent like CCl4 or chloroform or acetone, one of those things. So that is the interesting thing about osmotic pressure. Again, let me remind you, the process by which the solvent molecules distribute themselves is purely random. What happens here is the net effect. Because the concentrated solution has less solvent molecules, the osmotic, the movement doesn't stop, it keeps on going. But in the end, the net movement of particles from left to right uh, is predominant. Okay, so we have an equation for the osmotic pressure, and here we have it. All right, pi equals I m R T. Let's see what these things are. Of course, I is the Van Hoff factor. Once more, if the solution had been made with electrolytes, you have an extra factor in there to increase the effect. Capital M is the molarity. Interestingly, for osmotic pressure, we use molarity. R is the gas constant, and T is the temperature. And once more, because we're involving the gas constant, we had to do temperature in Kelvin. I'm sure that in your homework, you're going to get some practice problems where they'll give you a solution and a temperature and ask you to calculate what the osmotic pressure is going to be. But I have a more interesting application because it's going to bring us back to way at the beginning when we started studying compounds. Remember that we said when you study compounds, one of your goals is to find out what is it made of, what is the formula of the compound. And we said that there are several methods for finding the composition of the compound. You can find the percent this, the percent that. And then once you know what elements are present, their percentage, you can find an empirical formula. But in order to find the actual real molecular formula, you need one more piece of information, and that is the molar mass. We have done several activities in our lab to find molar masses of unknown substances. I believe the last one we did was the classic Dumas experiment, where we found the molar mass of an unknown liquid by measuring its vaporization, right? So here comes another method for finding the molar mass, particularly of a non-electrolyte. If I know that a substance is a non-electrolyte, and this is particularly very useful for substances with large molecular weights, like proteins and these kind of like large molecular species. So here goes a problem. 17.5 grams of a protein, which is a non-electrolyte, are mixed with water to form a 0.500 liter solution. At 25 degrees Celsius, the osmotic pressure is 10.0 millimeters of mercury. What is the molar mass of the protein? See, I like this kind of problem. This is really cool because molar mass is something I want to find out if I want to know what the formula is of my compound. Now, here between you and me, it's a stretch because proteins typically have hundreds of atoms in there. I mean, these are really big molecules. So finding the formula of a protein really is not what we go after. Mainly people in the biochemistry field, what they like to find out is what is the sequence of the amino acids building blocks that are used to build a protein. But anyway, I'm kind of going off track here. All right, so here's our formula. Now, in this case, they give us a temperature. We know what R is. We have the osmotic pressure pi. We are told it's non-electrolyte. So what is our unknown in here? What are we solving for? Well, actually, that's the one we don't know. We don't know the molarity of this. But molarity is moles per liter. And since we have the number of liters, we can find out how many moles are in there. And if we know how many moles is 17.5 grams, we can find out how many grams is 1 mole, right? All right, let's do this. So let's rearrange our equation here, and that's what we're going to do. Some of the values, let's put them in. So R is 0.08206 liters times atmospheres per mole per Kelvin. That's our good friend, the gas constant. Temperature has to be in Kelvin, so we're going to add 298 to our 25. I'm sorry, 273 to our 25 to get 298 Kelvin. And pi is 10 millimeters of mercury, but since R is in atmospheres, we had to convert that to atmospheres. And that gives us 0.0132 atmospheres. All right. So a lot of this is basically bookkeeping to make sure that we have everything in the proper units here. And the presence of R forces us to change other units into atmospheres and Kelvin. Okay, give me a chance to write that down. And let's go ahead and see what we get. So let's put all the numbers in here. So we said we had 0.0132 atmospheres. What is the value of I? Right, it's 1. It's a non-electrolyte, so we're going to say I equals 1. R, we have it. Temperature is 298. Let's put all those things in there. Make sure you put the units. Just because you're almost finished with this class doesn't mean that you still don't have to make sure the units cancel out, right? Don't get too cocky with that. All right, so atmospheres cancel out, Kelvin cancels out. And so what I have is I have in the bottom there liters over moles, which is going to flip to give me moles per liter, which is what I want. All right, let's do the calculations. And the calculator says, okay, so 5.40 times 10 to the negative 4 moles per liter. You could tell based on the numbers on the top there that it was going to be a small value. Remember, like I said, proteins have very large molar masses. So a sample of a few grams of a protein is going to have very, very few moles in it. So in a half a liter solution, that's a small value of molarity. So this gives me the moles per liter. So let me see what the molar mass is going to be. So I'm going to have a sample that was 17.5 grams divided by the moles. How do I get the moles? Well, I multiply the molarity times the volume. So that's 5.40 times 10 to the minus 4 moles per liter times 0.500 liters. So the liters cancel out. So notice that it is set up to give me values of grams per mole. And like I told you, it's going to be a pretty big number. It's going to be, drum roll, 6.48 times 10 to the 4. In other words, 64,800 grams per mole. In the field of biochemistry, when you do protein studies, we sometimes refer to the grams per mole as Daltons. So you might see this, said as or written as, 64.8 kilodaltons. That's the way biochemists usually say it. Okay, a few more seconds for you to write that down and get your notes. And let's finish out by looking at some applications of osmosis. Number one, how do you keep celery crisp? By storing it in water so that it's fresh and crisp for weeks. Well, remember, it's all about which side of the quote unquote membrane you're going to have more solvent on. So pretend the celery crisp is a bunch of cells protected from the exterior by, cell walls and membranes, and you put water on the outside. Of course, the interior of the cells have solutes in them. That means that which way is the water going to move? Right, it's going to move into the cells of the celery, therefore keeping it, plump, fresh, and crisp. I don't know this for weeks thing, but hey, if it works, that's good. Okay, another application is something called hemolysis. Now, I don't know if any of you are ever going to get a chance to do some little, undergraduate or graduate research in a tissue culture lab. But one of the things that scientists have to be careful about is they have to make sure if they want to have a culture of cells, they have to put them in the right medium. So for example, red blood cells, if they are placed in something called an isotonic medium, in other words, it's a medium where the concentration of salts and solutes in the salt and outside is the same as inside the cells. The red blood cells have the shapes that you can see there on the top. They look like little, I don't know, Cheerios maybe. Now, you can do other things, like, for example, you can change the medium and make the medium what is called hypotonic or hypertonic. Hypotonic means that you have, less solute on the outside than on the inside of the cell. So that means that water moves into the cells because they're more concentrated, and they cause the cells to plump up, like you see there in the middle picture there. You can also put the culture in what's called in a medium where you have more salts on the outside than you have on the inside, right? And then what happens is the water moves from inside the cells to the outside and causes the cells to kind of shrivel or wrinkle up. They call that crenation. So this is another example. You remember I mentioned when you put an IV on a person, remember we have to put some measure of solutes in there, some salt in there. I think it was 0.9%. Same reason. If you put just simply water inside your bloodstream, what's going to happen is the water is going to go inside your cells and cause your cells to kind of like, plump up and give you major inflammation. Okay, the last application here that we can think of is the water transport in plants. Of course, plants inside have a major system of, pipe and duct work, and that you'll study in biology what they call, the xylem and the phloem and whatever. But essentially, these are conduits that take water from the bottom of the tree all the way to the top. But essentially, at the roots, what the plants do is they concentrate solutes in the roots inside, so that water will, by osmosis, flow into the roots themselves. Hey, I know I was thinking of something. I think I just forgot to say. Okay, so the medium, I don't know if I said it or not, but the medium where the salt concentration are the same inside and outside is called isotonic, where you have, sorry, where you have higher concentration on the outside than the inside, you got a hypertonic. And then if you have lower concentration on the outside, we call it hypotonic. All right, so just in case I forgot to that. Okay, that has been our survey through colligative properties. And once more, I encourage you, whenever you go out there and go through the experiences of life, whether you're working with detergents, or you're working with oils, or you're working with salts, or you're cooking, or you're doing cleaning, or you hear about people talking about medical conditions and stuff, a lot of these things, they all boil down to the properties of mixtures and specifically solutions, because a lot of the chemistry that we observe out there happens in solutions. Now, there's a section of this chapter that has to do with other types of homogeneous mixtures, suspensions, colloids, gels, and stuff. I am not going to hold you responsible for that section there. So basically what we'll do is we will let you read that on your own, just for your own education and culture, but you are not responsible for these things, okay? So I'm gonna take a few moments here in case you have any questions, and then we will be dismissed.